The main clue that we are using and know that it is going to be inverse trig is that the degree of the denominator is going to like beat the degree of the numerator by more than 1. So you're looking at like kind of the largest exponent and going from there. There's 3 inverse trig functions you have to know. You have to know arctangent, the arcsine one, and then the arcsecant one. We looked at some examples on Friday. The first example I didn't quite get to is going to be the one if you're following along in OneNote. It says arcsecant with a twist. So I want to do this one, and then we'll look at some of the other cases. Looking at this one, I have the integral of dx over 5x on the square root of x squared minus 7. So let's kind of talk about first off how we know that this is going to be inverse trig. I know that this is inverse trig because I'm looking at the degrees. The largest exponent we see in that denominator is 2. And then there are really no variables in that numerator, so we know that the largest exponent is 0. So that's going to be our first clue that it is inverse trig. We have 3 options to choose when it comes to inverse trig. We have arcsecant, arcsine, and arctangent. I can rule out arctangent pretty easily because I see the square root sign and the minus sign. Arctangent has no square root and a plus sign. And then the one that has a square root is either going to be arcsecant or arcsine. Arcsine is going to be an example if I go to one from Friday. In arcsine, you're always going to be subtracting the variable inside the square root sign. An arcsecant problem will be the one that we're looking at now, clearly because it says that. But arcsecant will always have the variable come in front of the minus sign. The other thing that's going to have to be true when we're looking at arcsecant is whatever is being squared has to match exactly on the outside. So yes, we see that 5x on the outside, but what's really making this an arcsecant problem is I see we have x squared and that x is on the outside of the problem. So if I go to integrate this one is going to be with the arcsecant formula. We know for all these inverse trigs, it's a little bit different from all the other rules, because not only do we have to sometimes be worried about u substitution, we often have to find the a value. In all the previous examples we did on Friday, that a value was a whole number. It doesn't have to be a whole number. So for example, I'm looking at this one, what number squared is going to give you 7? Square root. So I know that a is going to be the square root of 7. Don't need to worry about u sub for this one because it's just an x squared. So I can go ahead and jump straight to my arcsecant rule. So I have this 5 in the denominator that's going to kind of carry across. So I have a 1/5 kind of built in from the problem. And then I'm going to go ahead and use the arcsecant rule. So I have 1 over a arcsecant, absolute value of x over a plus c. The arcsecant one is kind of weird because it does have the absolute value signs in it. And then this one kind of has 2 things to be careful with. That 1/5, which is just coming from that 5 in the denominator. And then we have the 1 over a coming from the 7. That's kind of like a direct application of that rule. Questions on that one? All right, the next one I didn't get to, that I wanted to do is actually, this next one. Degrees differ by a lot. So first off, the main reason why we know that we are going to be doing an inverse trig problem is an inverse trig problem is going to be obvious to us when the degree of the denominator is bigger than the degree of the numerator by more than 1. So like in all the other examples, it's just been bigger by like 2, but it is going to be true whenever you see it bigger by more than 1 anytime. So this is going to be a case that I think is the most obvious inverse trig because we have a degree of 14 being compared to a degree of 6. 14 is much bigger than 6, so the only way we're going to be able to deal with a problem like this is going to be inverse trig. I do think it's helpful when you're doing inverse trig to kind of force it to look like an inverse trig problem. So if you're just looking at the arrangement of this one, like I see the square root sign, so I know it's not going to be arctangent. Based on the order we see the variable being subtracted, this is going to be more of an arcsine problem and an arcsecant problem. Arcsine. Also, we know it's an arcsine because there's nothing directly outside that square root sign. So if I want to make it look more like an arcsine problem, I need to figure out like what squared is going to give me that 9x to the 14th. Well, what squared is going to give you 9x to the 14? 3x to the 7th. Remember, when you're doing exponents, power raised to the power, you multiply. So we're looking at this one. I'm going to make that 4 look a little bit more like a 4. Kind of different things we're looking at. I do have the a value still. What squared is 4? 2. So I know that a value is going to be 2. And then we also need to worry about u sub for this one. U would be 3x to the 7th. And then go ahead and find u prime. What's the derivative of 3x to the 7th? 21x to the 6th, which is what we wanted, because we want this x to the 6th to cancel out with the x to the 6th that is in the problem. Many of you could probably get by without showing this next step. I'm going to kind of show it so we can see it. I have the integral. So the x to the 6th is canceled, so I have 1 over the square root of 4 minus u squared du over what's left out with the u prime. Now it is very obviously an arcsecant problem. So this x to the 6th is canceled. So now integrating this one, we have a 21 left over in the denominator. So I have a coefficient of 1 over, is it 27? 21. This is arcsine. Arcsine is the oddball out. There is no 1 over a for arcsine, so I can go ahead and jump into the word. So I have the arcsine of u, what was u, 3x to the 7th over a plus c. So again, kind of strategy with that one, first recognizing that it is inverse trig, forcing it to look like inverse trig, and then doing the correct u substitution. Questions or things I can clarify about that one? All right, we'll keep moving along. Next two examples. These two I will say, I think when I shared the notes with you on OneNote, if you are following along in OneNote, I think they're on 2 separate slides, and then I combined them into one slide after I shared it. These are probably the two that I would think are like tricky, and honestly, they're not obvious that they would be an inverse trig problem. And we'll talk about why they're tricky, because again, I do think they are a little bit tricky in the way that they work out. So if you were to look at these problems normally, like even before you learn the inverse trig rule, I could definitely understand why a student would see these as like another rule. Like this first one looks like a problem that you should be able to rewrite with a negative exponent, like with a negative 1/2 exponent. I would understand if you think it should be done that way, but that's why we always want to check to see if that u sub is going to work out or not. If, and this is a big if this was a problem, I would rewrite with a negative 1/2 exponent. We would let u be the entire denominator. And this is where we see the u prime not working out. When I do the derivative of what's inside that square root sign, the denominator, 4 is a constant, so it goes to 0. We have a negative. Taking the derivative of sine squared does require the chain rule. So like the 2 is going to come down in front. Inside stays the same, times the derivative of the inside. And now you can kind of clearly see that u prime, much more complicated. That u prime is not going to cancel out with just a cosine. So like if it all else fails, like if you don't know how to start the problem, like try to let u be something. If u doesn't work that way, then try something else. So like u doesn't work this way, we're going to toss it. And for us in this class, thankfully we don't have like a ton of different methods to look at. The only other option where we have is like, well, if that u sub doesn't work, let's try an inverse trig u sub. If this is going to be an inverse trig u sub, remember we don't set the entire denominator equal to u, or like what's inside the radical equal to u. We only set what is squared as your u. So let's talk about why this might be inverse trig. If this is an inverse trig problem, what inverse trig formula does it look closest to matching? Arcsine. So we have a square root, we have a minus sign the square root, and the variable comes second. So it looks like arcsine. I can go already kind of identify this for a would be a 2 value. What would be my u? Well, what's being squared? Sine is what's being squared. So what would be u prime? U prime would be cosine, and that u prime makes us a lot happier because that cosine is going to cancel out. Again, you could skip this step. I'm going to write it out, but I have the integral of cosine of x over the square root of a squared minus u squared du over u prime. Cosines cancel out, and then it is very obviously an arcsine rule. Remember, arcsine doesn't have 1 over a in front, so when I jump to the rule, I'm just going to jump into the arcsine of u over a plus c. So again, why I consider that one tricky is it looks like it should be one you can rewrite the negative exponent, but it's actually an inverse trig problem in disguise. This second one, I also consider to be a tricky one. In fact, it looks a lot like a problem you had on your quiz. Don't remember the number, but I know it was like the middle problem on that page. It looks like it should be integrated using what rule? What's the denominator raised to? What power? The first power. So it looks like to me, like, again, I know the calculus teacher, but to me that looks like it should be an obvious natural log rule. Like the denominator is raised to the first power. There's something else that could potentially cancel. If it was the natural log rule problem, then your u sub should work out correctly. And if you let u be that entire denominator, again, no shame in letting u pretend to be something for now, even if it doesn't work out. What would be u prime? Well, the derivative of e to the 4x is just e to the 4x times the chain rule, so times 4. Looking at this, that e to the 4x is not canceling out with e to the 2x. So we're sad, this is not the natural log rule. When it's not one of the rules that we expect it to be, I'm going to tell you to see if you can force it to be an inverse trig rule. What inverse trig rule does that look like it could be closest to? Arctangent. There's no square root sign and plus sign. Easy kind of arctangent one. So let's force it to be arctangent. I like putting my number in front, so I'm going to have 3 plus, and I want to think of e to the 4x as something squared. Well, what squared is going to give you e to the 4x? E to the 2x, again, power to a power means you multiply. 2x times 2 will give you 4x. What will be our a value? Well, what squared is going to give you 3? Our a value would be root 3. Our u is going to be what's being squared. Well, technically, e to the 2x is being squared. So what would u prime be? Don't forget the chain rule, e to the 2x times 2. Now, after doing the substitution, I think it becomes a little bit more obvious that this actually is an arctangent. So I have the integral of e to the 2x over 3 plus u squared. dx is du over u prime. Now the e to the 2x's cancel out correctly. And we can go ahead and jump into the rule. So I have this over 2 that I don't want to forget about. So I have 1/2. Arctangent does have 1 over a in front. So I would have 1 over a out in front. And then this is the arctangent. What is it the arctangent of? It's the arctangent of u over the a, and then don't forget your plus c. So again, I do think those are tricky ones. They're not obvious to, I think, many students that those are inverse trig. But again, just like try something. If your u prime is not working out, then see if you can force it to be an inverse trig problem. Any questions from those two, from anyone here in person or at home? All right, now let's do the real fun ones. Completing the square. So let's just go ahead and get it out of the way. Completing the square is not as bad as you think it is. Let's talk about why it's needed. It is used to basically manipulate an algebraic expression. Ways we have used completing the square before. I think when it's first taught in Algebra 2, you like solve an equation by completing the square, which honestly, no math person solves an equation by completing the square. You kind of lied to, but hey, it works out. Why we do actually completing the square is it helps us to manipulate expressions. The last time you probably completed the square, I know you definitely did it when you had me, if you had me last year, was in the conic sections unit. So it was allowed us to manipulate like an algebraic expression and write it as like something squared. And that's going to be the idea when we're doing it with these problems. We want to basically force it to match up with an inverse trig problem. And so this is the one I want to look at. We have the integral of dx over this x squared plus 6x plus 10. Before we even start this problem, let's just get it out of the way. How do I know that this is even inverse trig? There's no point in completing the square unless it is inverse trig. Looking at the degrees. The degree of the numerator is 0. There's no variables there. The degree of the denominator is 2. The denominator is winning by more than 1, so it does have to be inverse trig. But right now, it doesn't look like any of the inverse trig kind of formats. We have 3 terms, which none of them have like 3 separate terms in the denominator. If you had to guess, which inverse trig formula do you think we're going to use eventually? Arctangent. So there's no square root signs. So eventually, I want it to look something like the integral of 1 over a squared plus u squared. Like that's the goal. Right now, like that 6x is kind of in our way. How do we get this to be in the correct format? I like going off to the side because I think it gets messy when you try to work inside the integral. I want to complete the square for that polynomial. So when I complete the square, write it in standard form. So write the x squared term, the linear term, and then the constant. So I have x squared plus 6x. I leave a gap plus 10, and then a gap after the 10. When you complete the square, does anyone remember what you have to add to complete the square? B over 2 squared, right? So the formula, if you need the reminder, is often just described as you're adding b over 2 squared. What is that b? That b is the coefficient you see in front of the linear term. So in this case, it would be x. So I am going to add that 6 over 2 squared. But we can't change the problem. Like you can't just say like, oh, I'm going to add 6 over 2 squared and be done with it. You can't change the problem, so we do want to balance it out. So like if I've added it, then I also just have to immediately subtract it because I can't change the problem. So technically we're adding 0. We're just doing like a fancy 0 where we add and subtract it. If you had me last year, this was typically context you had like an equal sign. So what you did to one side of the equal sign, you did to the other. But for us now, since there's no equal sign, we just have to kind of like add it in one place and subtract it later. So we're just adding 0, but it's just a fancy 0. Why does completing the square work? I'm going to show a middle step that most of you are going to skip from now on, because it kind of shows you why it works. But we have the x squared plus 6x. 6 divided by 2 is 3. 3 squared is 9. And then we have plus 10 minus the 9. Again, that, what I have in green, is still the same denominator. The first 3 terms is when we call it completing the square. We force that to be a perfect square trinomial. 2 numbers that multiply to give you 9, but add to give you 6 is 3. So that's the same thing as saying x plus 3 squared. And then the last 2 numbers we can just kind of combine together. 10 minus 9, positive 1. Most students kind of go with the shortcut. What goes inside the parentheses is always going to be half of that original b value you see in the problem. So like if it's a plus, it's going to be a plus sign in the parentheses. If it's a minus, it's going to be a minus sign in parentheses, and always half that value. Do want to emphasize when people do the shortcut, they do sometimes forget to keep it balanced. So like remember, you always have to subtract that b over 2 as well. So that's all there is to completing the square. So what we've done is we've taken the denominator that was x squared plus 6x plus 10. That is equivalent to saying x plus 3 squared plus 1, which now is very obviously an inverse tangent, an arctangent rule. Technically have to think about u sub, but the derivative of x plus 3 is just 1, so it's not going to really matter. It is arctangent. A value is also technically 1, so we're not going to have a lot of coefficients for this one. So this answer is just going to be the arctangent of u over 1 plus c. And that's how we use completing the square for integrals. And you thought you were done with that. Questions on that problem, either like the answer or kind of like the process? All right, so I have one more question I want to do today. It's another completing the square one, but like most students are pretty comfortable with completing the square when it becomes an arctangent problem because there's no like minus signs, there's no square root signs. It does get a little bit trickier, not more difficult, but you have to be a little more careful with making a kid's mistake when it's like a square root and a minus sign. So the first thing that I should emphasize, and didn't do a too good job when I started this problem, but when you are completing the square, you always want your leading coefficient to be a positive 1. Like, it only really works out nicely when your leading coefficient's a positive 1. Oftentimes in a lot of these problems, it's not going to be a positive 1. So let's look at this example. So I have the integral of 5 over the square root of 4x minus x squared. Again, questions we should always get used to kind of asking ourselves. How do I know, how should you know that this is going to eventually be an inverse trig problem? And again, it goes back to the degrees. The degree of the numerator is 0. The degree of the denominator is 2. That denominator is winning by more than 1. So we know it has to be an inverse trig. Any guesses of what inverse trig formula that one's going to eventually use? Arc sine. It is going to be arc sine. Like, you can rule out arctangent pretty easily because you see the square root sign. It is going to eventually be arc sine. I know that because there's not really anything outside that square root. So it isn't going to be an arcsecant one. The issue, though, is if this is arc sine, it should look something like, well, that 5 is a coefficient, but I want something like the square root of a squared minus u squared du. Right now, what's causing that issue is this 4x term. If that had just been a 4, then we would be fine. We would know that a value is 2. But that 4x is kind of throwing things and messing things up. So this is what we want to rewrite. When I complete the square, like going off to this side. And this is what we are completing the square for. Again, you want to make sure it's kind of in standard form. So I'm just going to rewrite it and move that negative x squared in front, and then plus the 4x. And then before I start completing the square only works when your leading coefficient is positive 1. Well, I can't just make that negative disappear, but I can factor out that negative, changing that to a minus 4x to make it so I can complete the square. Notice I kind of put a big gap before I did the closed parentheses. I still need to complete the square inside of those parentheses. So now to complete the square, we know we're going to add b over 2 squared. So I'm going to go ahead and add 4 over 2 squared. I can't change the problem, so once I add it, I have to immediately subtract it. Rewrite it, simplify, and then integrate. So I have that negative still hanging out in front. The first 3 terms will become my binomial. So I'm going to have x. It's going to be a minus 4 divided by 2 is 2 squared. And then this last term, it doesn't have anything to add to it, but I have minus 4 divided by 2 is 2. 2 squared is 4. Remember that negative we kind of factored out and had out in front. I can redistribute it back across, and we end up with 4 minus x minus 2 squared. So we've taken 4x minus x squared and rewritten it. 4x minus x squared is equivalent to 4 minus the quantity x minus 2 squared. How is that useful? When I go to plug that back into the problem, it is now much more obviously an arc sine problem. Note arc sine, we're subtracting the variable, so we can go ahead and look at it. The a value does end up being 2. Technically, there's a u, but u prime is 1, so I don't need to worry too much about the u substitution. Just don't forget the 5 up top. So when I go to integrate this one, 5 is a coefficient. Arc sine does not have 1 over a, so I have 5 arc sine of u over a plus c. And that will be your final answer. Questions on that process? Yes, Nick? Yeah, go ahead. Questions on that though? Go ahead. Arc secant is the only one with absolute value. Arc sine would have the parentheses. Any other questions? All right, so if you're looking at OneNote, there is one more slide. That's going to be tomorrow's warm-up. In case you're just feeling extra, I want to do it now. That's tomorrow's warm-up. This is the calendar for the next 2 weeks, and there are just some things I do want to kind of point out to you just to make sure we're all on the same page. So we've really finished the notes. I really have nothing else to teach you for this unit. You just need to make sure you practice and get really good at finding integrals. I'm going to ask you to try to do as much of homework 3 tonight. Obviously not due to your test day, but it'll just help you out if you can go ahead and get as much of that done tonight. Tomorrow, in regards to that homework, I want you to come to class with homework questions. Like we'll do that warm up and I'll kind of open it up, kind of go over questions that you have. I will say some of those questions in homework 3 are tricky. And like I assigned them on purpose because I want you to be thinking about them. I fully expect questions on some of them. Whenever you finish homework 3, though, you can go ahead and just continue working on homework 0 and even start homework 4. There's no new material on homework 4, but it's just a bunch of integrals mixed together. Kind of get your brain used to switching between rewriting versus natural log versus inverse trig versus other types of integrals and get kind of used to that. Wednesday is going to be just a work day. Clearly comes questions. Did want to remind you, if you need to do the Unit 5 recovery, I will be offering that during office hours on Wednesday. Please either send me an email or a remind text if you do plan on taking it. Just make sure I have a test for you, either virtually or here in person. Thursday in class, just a review day, mainly working on briefcase binder or finishing up your homework. Yay for long weekends. Friday, no school. Monday, no school. Tuesday is just going to be a review day. Like, let's get stuff done. Let's make sure we are completely confident with what we have to do. And then testing on Wednesday. Yes, I know Wednesday is one of the shortened periods with just a 40-minute period, but I've purposely written the test to be done in 40 minutes. So like most of the time my assessments are at 40 points. This one is only graded at about 30. So it is going to be scaled down and not have as many questions. That does mean that each question is weighted more, but then at the same time, it does mean that there are less questions to get done. And then the last thing that I did want to say, this is for the next unit, but I just want to give a heads up. Unit 7 is probably one of the more challenging units that we have this semester. It's going to also be the first time, honestly, in calculus that we're going to rely a lot on the graphing calculator. So next week, like we won't begin it until Thursday, but we're going to do problems that require a graphing calculator. And again, when we say requires a calculator, it's not like, hey, use a calculator if you want to. It's literally, you cannot do the problem without the functions of a graphing calculator. I know many of you have a graphing calculator. If you don't, I need to kind of know ASAP so I can make sure I have one checked out for you. The school does have some that can loan out. That's especially important if you're virtual right now. We'll need to find a way to get you a graphing calculator before Thursday, because again, it is expected that you know how to use it, and you will need to use it starting the next unit. So that's kind of what you have to get done. I'm going to go ahead and let you get started with the homework. Again, please come tomorrow with a lot of questions for me. And yeah, that's it. If you do have questions you want to ask now, then like definitely don't hesitate to do that. But if you are at home, you can go ahead and leave the meeting.